This is the demonstration video for a data exfiltration method via Bluetooth Low Energy enabled smart bulb. During our research, L1ght found that a common Chinese firmware smart bulb had no authentication mechanism. This means that anyone can connect to the bulb via Bluetooth and change its colors, or even play sounds. We devised a case scenario where an attacker that has gained control over a device that has a Bluetooth radio and has a vulnerable smart bulb in its proximities to be able to use the vulnerable smart bulb and exfiltrate data in an unsuspecting way by slightly modulating the LED colors. Two prototype apps were developed, an emitter app and a receiver app. The emitter app is the raw code running on a compromised device. When the app starts, it starts to scan for Bluetooth-enabled smart bulbs. Once a smart bulb is found, the app enumerates the smart bulb services. After finding the color services, it connects to it and starts to exfiltrate the data that is on the box. In this case, it's secret. When the stealth button is off, the light changes in a visible way. It's kind of a test mode, so you can see that the app is really working. Or if you're doing some night operation where you're not worried about getting caught. When the stealth mode is on, the changes on colors are so slight that it's hardly noticeable by any user. As you can see on screen, the data rate is quite slow. This is because we are only using one light channel to encode information, which is the blue channel. I chose the blue channel because the human eye has trouble in differentiating different types of blue. It's easier for us to notice changes in red or green. There are several ways how we can improve the data rate. By encoding the information faster and on more channels because we are not using the red or green channel. The app loops until it's stopped on the exfiltration on-off button. The receiver app that we are going to see next uses the camera to decode the information. We had two choices, or use the camera or the ambient light sensor on the device. We chose the camera because it's more ubiquitous. Any device has a camera. As long as it's not very slow and can have some decent frame rate, we can decode information and use the CCD sensor on the camera. As you can see here, you can see the light flickering. It's not on stealth mode. You can see that the word secret is being decoded. You see the bits and bytes being slowly reconstructed back to the original word. The decoder, the app doesn't have to be pointed to the light bulb. You can just point to some area that is illuminated by it. As you can see in this image now, we're just pointing to the wall, and it's able to decode the information that's getting it. The app has three buttons: start-stop button to initiate the decoding process. The middle button allows a user to switch between resolutions. A lower resolution enables the app to get a higher frame rate. A higher frame rate always improves the decoding process. And also, you can choose to change the camera between the front and back camera. On stealth mode, as we can see here, it's very hard to see that the light is even changing. You see that the receiver is able to decode a slight change on the blue channel, but the user cannot tell that the light is flickering. You can see the word secret being slowly reconstructed back to the original. The lamp appears just to show how hard it is to tell that it's flickering or changing the blue intensity. As with the previous example, you just have to point the app to an area that is illuminated by this light. Luckily, the app is able to lock on the changes of values and start to decode the correct information. No error checking mechanism is in place yet. This is just a prototype app, and errors might occur. You just have to adjust the camera to a proper illuminated area. As you can see, the information comes in quite slow. It's around 6 bits per second. The emitter has to send the information quite slow. This is because the frame rate that we can achieve on the receiving device is not very high. If we get 30 frames per second, it's quite okay. Of course, there are several ways we could improve, like accessing the sensor of the camera in a native way, or use another receiver. In our example, we are just developing a regular Android app and accessing the preview component of the camera. Hard to see the light flickering at all. In this last test, I had to see how far can I take the prototype. So I decided to make a long-range test to figure out if it's sensible enough to receive information during the day at a considerable distance. So I improvised a telescope and connected to the camera of my phone. Now, this telescope is focused on my house window, and the distance is around 50 meters during the day. During the day, it's a bit harder to distinguish colors than during the night, but still, you can see that the prototype decoded the information pretty good. As a proof of concept, I'm fairly happy. So I used some duct tape, of course, as any good engineer would do. You can see my dog and you can see the house over there in the distance. Bye bye.